They don't want you to know this. On September 13th, 1995, Hurricane Marilyn tore through the Caribbean with sustained winds of 115 miles per hour. The island of St. Thomas lost 80% of its housing stock. Concrete homes cracked. Steel roofs became airborne debris. Wood-framed structures vanished into splinters. And in the middle of that devastation, a cluster of cylindrical buildings made from cardboard tubes stood completely intact. Not damaged, not compromised, untouched. The architect who designed them, a Japanese man named Shigeru Ban, had used the most disposable material in modern manufacturing to build the most hurricane-resistant emergency shelters anyone on that island had ever seen. The structures cost almost nothing to build. They required no skilled labor. They could be assembled in hours and disassembled just as fast. FEMA studied them. The United Nations deployed them, and then the construction industry did what it does best when something threatens the economics of conventional building. It looked the other way. Before we continue, I want to see how global this is. Comment your country. This is not speculation. Cardboard tube construction has been tested in disaster zones across 5 continents for nearly 3 decades. It has been peer-reviewed, published in engineering journals, exhibited at the Museum of Modern Art, and awarded the Pritzker Prize, the highest honor in architecture. The material science is settled. The structural performance is documented. The cost savings are absurd. What remains unsettled is why, in a country that loses tens of thousands of homes annually to hurricanes, tornadoes, and wildfires, almost no one building housing today knows this technology exists. To understand what Shigeru Ban discovered, you have to start with what cardboard actually is. Not the flimsy box your Amazon delivery comes in, not the single-wall corrugated sheet that collapses when it gets wet. Industrial paper tubes, the kind used to roll carpet, ship posters, or form concrete columns on construction sites. These tubes are made from layers of craft paper wound in a spiral under tension and bonded with water-resistant adhesive. The wall thickness can run anywhere from 1/4 inch to over 2 inches depending on the application. The diameter ranges from 4 inches to over 4 feet. And when manufactured to structural specifications, they possess compressive strength that rivals steel per unit weight. A 4-inch diameter paper tube with a wall thickness of just 15 millimeters can support over 2 tons of axial load before failing. That is not a theoretical number. That is a tested, published, repeatable result from structural engineering labs. Scale that tube up to 12 inches in diameter, and you are looking at load-bearing capacity that exceeds what most residential wood framing can handle. The tubes are lightweight, which means no heavy equipment needed for installation. They can be cut with a handsaw. They slot together with simple joints. They require no welding, no bolting, no specialized fasteners. A crew of untrained volunteers can erect a paper tube shelter in less than a day. But strength alone does not explain why these structures survive hurricanes. What makes them resilient is geometry. Ban designed his emergency shelters using a cylindrical form because cylinders distribute wind load in a fundamentally different way than rectangular buildings. A conventional house presents flat surfaces to the wind. Those surfaces create pressure differentials that generate uplift on the roof and lateral forces on the walls. The sharper the edge, the more turbulent the airflow, and the greater the destructive force. A cylinder has no edges. Wind flows around it. The pressure equalizes. The forces that would rip a roof off a wood frame house simply slide across the curved surface of a paper tube structure and dissipate. This is not a new discovery in aerodynamics. Engineers have known for over a century that curved forms shed wind more effectively than angular ones. It is why grain silos survive tornadoes that obliterate the barns next to them. It is why lighthouse structures endure coastal storms. Shigeru Ban just applied that principle to housing using a material no one thought belonged in construction. The first large-scale test came in 1995. Not with Hurricane Marilyn, but in the aftermath of the Kobe earthquake in Japan. Over 6,000 people died, more than 100,000 buildings were destroyed. Survivors were living in crowded evacuation centers with no privacy, no dignity, and no timeline for permanent housing. Ban proposed paper tube partitions to create private spaces within the shelters. The local government rejected the idea. Paper was not a building material. It would not last. It was undignified. Ban built the partitions anyway using donated materials and volunteer labor. Within weeks, evacuees were requesting more. The structures worked. They provided exactly what was needed: temporary, functional, humane shelter that could be erected immediately and removed without waste when permanent housing was ready. That same year, when Marilyn hit the Caribbean, Ban adapted the design for tropical storm conditions. He used larger diameter tubes, spaced them closer together, and added a tensioned fabric roof that flexed with wind gusts instead of resisting them. The result was a structure that weighed a fraction of what conventional emergency housing weighed, cost less than a tenth as much, and survived wind speeds that destroyed everything around it. FEMA noticed. So did the United Nations High Commissioner for Refugees. Paper tube shelters were deployed in Turkey after the 1999 earthquake, in India after the 2001 Gujarat quake, in Sri Lanka and Thailand after the 2004 tsunami, in Haiti after the 2010 earthquake, in the Philippines after Typhoon Haiyan in 2013. Every deployment proved the same thing. The structures performed. They lasted longer than expected. They cost less than any alternative, and they could be built by the people who needed them without waiting for contractors, permits, or supply chains. So why, 2 decades later, are American disaster relief agencies still deploying FEMA trailers that cost $50,000 each, take months to manufacture, and require flatbed trucks to deliver? The answer starts with a single uncomfortable fact. The global construction materials market is worth over $1.3 trillion annually. Lumber, cement, steel, and glass account for the overwhelming majority of that spending. Cardboard tubes are manufactured as industrial packaging, not building components. There's no lobby for them, no trade association, no billion-dollar supply chain optimized to push them into residential construction. The material exists in a category the building industry does not recognize as legitimate, even when the engineering data says otherwise. The University of Bath's BRE Center for Innovative Construction Materials tested paper tube columns under load conditions that would be considered extreme for residential framing. They subjected the tubes to compressive forces exceeding 20 tons per square meter. The tubes did not buckle. They did not deform. They held. The published study noted that paper tubes, when properly treated and sealed, demonstrate structural performance comparable to timber in compression applications. That data has been publicly available since 2008. It appears in peer-reviewed engineering journals that every structural engineer with a university library login can access before lunch. And yet, when California's Camp Fire destroyed Paradise in 2018, the Federal Emergency Management Agency deployed the same metal and plywood temporary housing units they have been using since the 1970s. Structures that cost taxpayers tens of thousands of dollars each require months to fabricate and generate mountains of waste when they are eventually dismantled. The friction is not technical, it is categorical. Building codes in the United States are written around recognized material classifications: wood, concrete, steel, masonry. Those categories have testing standards, fire ratings, load tables, and entire sections of the International Building Code dedicated to their proper use. Cardboard does not appear in that list. It is not that code officials have evaluated it and rejected it. It is that the regulatory framework does not have a place to put it. A builder who wants to use paper tubes in a permitted structure has to navigate the alternative materials approval process, which requires independent testing, engineering stamps, and often months of back and forth with local inspectors who have never seen the material used structurally. That is not a technical barrier, it is an administrative one, and administrative barriers, unlike engineering problems, do not get solved by better data. They get solved by economic pressure or by systems breaking down so completely that alternatives become unavoidable. Shigeru Ban has built permanent homes, schools, and churches from paper tubes in Japan, New Zealand, and France. The cardboard cathedral in Christchurch, New Zealand, constructed after the 2011 earthquake that destroyed the city's historic stone cathedral, was designed as a temporary structure with a projected lifespan of 10 years. It is still standing. It seats 700 people. It hosts weddings, funerals, and concerts. The A-frame roof is supported entirely by 98 cardboard tubes, each 24 inches in diameter and 70 feet tall. The structure has survived multiple aftershocks and a decade of New Zealand's coastal weather. It was built in less than 2 years at a fraction of the cost of conventional reconstruction. When the city eventually builds a permanent replacement, the cardboard cathedral will be disassembled and the tubes recycled. No demolition crew, no landfill, no debris field. Meanwhile, across the Pacific, American cities continue to debate whether they can afford to rebuild after hurricanes, whether they can house their homeless populations, whether disaster survivors should wait 2 years in temporary trailers for permanent housing. The question is never whether a faster, cheaper, less wasteful alternative exists. It is whether that alternative fits into the procurement systems, the supplier relationships, and the material categories that the construction industry has spent a century optimizing around wood and concrete. There is a second factor that does not appear in engineering reports but shapes every decision a contractor makes. Liability. A builder who uses dimensional lumber knows exactly how that material will be treated by insurance adjusters, code inspectors, and courts if something goes wrong. The risk is quantified. The precedent is established. A builder who uses paper tubes is introducing a material with no legal track record in American residential construction. If a structure fails, if an occupant is injured, if an insurance claim is denied because the material was unconventional, the liability does not fall on the material manufacturer. It falls on the builder. That is not an irrational fear, it is a structural reality of how construction risk is distributed in the United States. And it means that even when a material performs better, costs less, and generates less waste, builders will default to conventional choices because those choices come with legal cover. The incentive structure is not designed to reward innovation. It is designed to minimize individual liability, which is why the only place paper tube construction has gained consistent traction is in disaster zones where the conventional system has already failed, when there are no houses left to insure, no supply chains to rely on, and no time to wait for lumber shipments. The regulatory and liability concerns that would normally block an unconventional material suddenly become irrelevant. People need shelter now. The material works, it gets used. Then, the moment the crisis passes, the industry reverts to wood. This is not unique to paper tubes. Rammed earth construction, a technique where soil is compressed into solid walls without any binder, has been used to build structures that have stood for centuries in every climate zone on Earth. The Great Wall of China includes rammed earth sections that are over 2,000 years old. Adobe homes in the American Southwest regularly survive 400 years with minimal maintenance. The material costs almost nothing. It requires no factory. It performs exceptionally well in both thermal mass and compression, and it is virtually absent from modern American construction outside of niche custom builds. Why? Because soil is not a recognized structural material under the International Building Code. Because there is no commodity market for dirt. Because no manufacturer benefits from promoting it. The knowledge of how to build with it still exists, taught in specialized workshops and used by a small community of natural builders. But it does not scale because the industry is not structured to let it scale.